I'm Zach Baker, I'm a mechanical engineer.
Hi, I'm Shane Callahan, and I'm a mechanical engineer.
Hi, I'm Caitlin Kreider, and I'm a mechanical engineer.
Hi, I'm Ryan Schenkel, and I'm a mechanical engineer.
Hi, I'm Jenna, and I'm a mechanical engineer. The investigation of a solar-powered Stirling engine is significant to our understanding of thermodynamics, kinematics, finite element analysis, and the electric power generation. The energy relationships in the heat transfer, translational motion, and rotational motion that power the system are analyzed in an attempt to find optimal conditions. Being that the heat source is solar radiation, this design is aligned with societal renewable energy efforts. Considering all constraints and requirements, our design aims to accomplish a solar-powered Stirling engine. 7 watts of power is required for the DC generator, and frictional losses are assumed to be 2 watts. So the goal power output of the engine is 9 watts, and the Stirling engine must output 1 Newton meter of torque from the flywheel. The thermodynamic analysis of the working fluid and the kinematics analysis of the 2 crank slider mechanisms were complete. EGG code was created to solve thermodynamic cycles. MATLAB code was created to solve kinematic and kinetic relationships. Using Arduino and a breadboard, a circuit was created to measure temperature within the system and output power. Heat transfer of the system is being analyzed using finite element analysis methods.
The user requirements and the engineering constraints for this project overlap big in that the sun is the biggest factor in both of those categories. The solar-powered Stirling engine will not run without sunlight to power it. The sun is reflected off of a 13-inch parabolic mirror, and that parabolic mirror is then focused onto a heat sink, which will use natural convection to heat the hot end of the Stirling engine. And Shane will talk more about that coming up.
As Ryan had briefly mentioned, the natural convection will vary off of wind speed, and this will be correlated using the Bernstein-Churchill equation.
The Stirling engine is powered by a temperature difference. The temperature difference has a positive linear correlation to the power output of the engine. Increasing the compression ratio will logarithmically increase the power output. The assumptions are ideal gas law and no friction. The Stirling engine is analyzed using the ideal Stirling cycle, which is comprised of 2 isothermal and 2 isochoric processes. For the first process, there's isothermal compression with heat removal. The second process is isochoric heat addition to increase the temperature of the fluid and thus increase the pressure, which will push the power piston up. Third process is isothermal expansion with heat addition. And the fourth process is isochoric heat removal to decrease the temperature of the fluid and thus decrease the pressure, which will push the power piston down.
In our kinematic analysis, the power input is from the thermal expansion acting on the power and displacer pistons, with a torque and acceleration input from the flywheel at the origin. The 2 crank slider linkages have an offset of 0, meaning that the slider is acting along the x-axis. The graphical and analytical analysis of the positions, velocities, and accelerations, as well as the forces of each linkage, has been completed using Grashoff's law, material properties, instantaneous center of velocity graphical methods, and analytical equations solved using MATLAB code.
As the engine turns, the crankshaft rotates within a coil. The rotation of the crankshaft induces an electrical potential across the coil, making the coil act as a power source. At this stage, we're attempting to generate a voltage of about 7 volts to power small electronics such as a phone charger. This can, of course, be scaled up to generate more power for larger devices. The power needed for the DC generator is 7 watts because the current required for the charger is 1 amp.
Our plan for next semester is to refine our prototype in both design and materials. We will be experimenting with different plastics and metals, with an emphasis on overall quality and power output.